Linear Algebra, Section 1.2, Row Reduction and Echelon Forms. The definition of echelon form or row echelon form is threefold. First, all non-zero rows are above any rows of zeros. A non-zero row would be one that contains at least one non-zero entry. Secondly, each leading entry of a row is in a column to the right of the leading entry of the row above it. And we'll look at some examples in a second. And then thirdly, all entries in a column below a leading entry are zeros. So here are some examples of echelon form. The black box would be the leading entries, and they're the leftmost non-zero entry in each row. And then our stars would be any value including 0. So it doesn't have to be non-zero. But these are in echelon form. And notice that we've got our leading entry and every entry below it is 0 in this case. And then any row that has any non-zero elements in it is above all of our 0 rows, the rows that have all zeros. And then the leading entry here is to the right of the leading entry in the row that's above it. Okay, and we see the same stuff happening in our second matrix here. So these are in echelon form. This is another example of echelon form. You'll notice that our first column is got all zeros, and that's okay. The leading entry then in that first row is then the first non-zero entry, or the leftmost non-zero entry, so that we've got our box here. But this is also in echelon form. Then we have what we call reduced echelon form, and we add in the following conditions. Number 4, the leading entry in each non-zero row is a 1. Each leading 1 is the only non-zero entry in that column. So here's another example. This is the last one we looked at from the prior slide. And now we're going to take that echelon form and convert it to the reduced echelon form, adding in those last two conditions where the leading entry, our boxes, are all now 1s, and then above each leading entry we have zeros above and below, so it is the only non-zero entry in that column then. Now notice we could have non-zero entries in these other columns, but as long as the zeros are the only thing above or below our leading entry. Let's look at Theorem 1, uniqueness of the reduced echelon form. Each matrix is row equivalent to one and only one reduced echelon matrix. Here's some terminology. A pivot position is a position of a leading entry in an echelon form of the matrix. So remember that when we were looking at our matrices before, the leading entries were our black boxes. So then these are the pivot positions. A pivot is a non-zero number that either is used in a pivot position to create zeros or is changed into a leading 1, which then in turn is used to create zeros. And then the pivot column is a column that contains a pivot position. So in this case our pivot columns would be column 1 and column 3. Example 2, we want to row reduce to echelon form and then locate the pivot columns. So here's our matrix, and the first thing that we're going to do is interchange rows 1 and 4. That will give us a leading 1 in the first row. And so now this is our pivot. So that means that this is our pivot column. And what I want to do is I want to use that pivot, our leading one here, and create zeros beneath it. So I want to multiply it by 1 and add it to the negative 1, or to the row beneath it. And then I'll also multiply it by 2 and add it to the third row in order to get a 0 there. And we do that with all of the other entries, and we see we get the following matrix. So now I'm done with the first row, and I'm kind of looking at a new matrix, submatrix if you will. And I have a new pivot position and a new pivot column, so column 2. So my 2 is now my pivot position, and I can leave it as a 2. And what I want to do is I want to change the 5 and the negative 3 into zeros. So the first thing I'm going to do is I'm going to multiply this 2 by a negative 5/2 and add that then to the 5. And that will give me a 0. And then I'll multiply by a positive 3/2 and add it to the negative 3, and that'll give me a 0 there as well. And we do the same thing throughout, and we get the following matrix. So now I'm done with the first 2 rows, and I have this sub-matrix here because I've got zeros here, and notice then I've got an entire row of zeros, and to be in echelon form then those zeros need to be below my non-zero row here. So I'm going to interchange those 2 rows, and then I am now in echelon form. Notice that my pivot columns were column 1, column 2, and column 4. And if we look back at the original matrix, we've still got the same pivot columns, and our pivot positions were 0, negative 2, and 3. Those were the pivot positions. In example 3, we want a row reduced to echelon form and then to reduced echelon form. So here's my matrix, and the first thing that I'm going to do is I'm going to interchange row 1 and row 3. Row 2 stays the same. So now this is my pivot column, and the 3 is my pivot, because that is my pivot position. And so what I want to do is I want to turn the 3 into a 0 so that I have zeros beneath it. So what I'm going to do is I'm going to multiply here by a negative 1 and add that to the row beneath it. So I'll do that work off to the side. When I multiply by a negative 1, I'll have negative 3, positive 9, negative 12, positive 9, negative 6, and negative 15. And I'm going to add that to the second row, which was 3, negative 7, 8, negative 5, 8, 9. So I'm going to add those 2 together, and I'll get a 0, which is what I was wanting in that position. And then I have positive 2, negative 4, 4, 2, and negative 6. So I'm going to rewrite my matrix, and I'm going to replace row 2 with the row we just came up with. 0, 2, negative 4, 4, 2, and negative 6. And the rest of the matrix remains what it was. So now I'm done with row 1, and I'm using this lower portion now kind of as my new matrix, and the 2 here then becomes my new pivot. And so then column 2 is my new pivot column. So what I'm going to do is I'm going to multiply by a negative 3/2. This is multiplying row 2, and add it to row 3. And when I do that, that will give me a 0 here. So multiplying by negative 3/2, I'll have 0, negative 3, 6, negative 6, negative 3, and 9. I'm going to add that to row 3. So I'll have 0, 0, and then you'll notice that we continue to get a 0 and another 0. Then I have 1 and 4. So this is now my new row 3. So I'll rewrite my matrix again. Row 1 remains the same. Row 2, and now I've got this for row 3. 0, 0, 0, 0, 1, 4. And now we are in echelon form. So you notice kind of my stair step here. Where the 3, 2, and the 1 are the leading entries. And we're done here. So this is echelon form. We did not need to try to turn the 3 and the 2 into 1s. When we do that, that's getting us into reduced echelon form. This is the end of what we call the forward phase. So now we have the backward phase where we want to create reduced echelon form. And this is what I want you to work on, beginning with the rightmost leading entry and working upwards to the left. So you're going to begin with the 1 and you're going to work upwards and then go left. I want you to make the leading entries 1s, which this one already is, and then create 0s above it. So you'll need to create a 0 here and a 0 here. Then you'll need to turn this 2 into a 1 and work upward and turn the -9 into a 0 and then turn the 3 into a 1 as well. So I want you to get into reduced echelon form. This I want you to work on and bring to class with you. Now we apply this to solutions of linear systems. Here's a few definitions. A basic variable is any variable that corresponds to a pivot column in the augmented matrix of a system. And a free variable is all non-basic variables. So for example 4, we want to consider the augmented matrix. If we convert it to equation form, then we will have x1 plus 6x2 plus 3x4 equals 0. And then my second row, I have x3 minus 8x4 equals 5. And then my last one, I have x5 equals 7. So when we look at our augmented matrix, we notice that we have a pivot column here, here, and here, with the 1s being our pivots. So these are our pivot columns. And it turns out to be columns 1, 3, and 5. And notice then that the variables that corresponds to, it corresponds to x1, x3, and x5. And so then those are now our basic variables. They correspond to the pivot columns. And then the free variables are all the non-basic variables. So that would be x2 and then x4. The final step in solving a consistent linear system, after the augmented matrix is in reduced echelon form and the system is written down as a set of equations, then we solve each equation for the basic variable in terms of the free variables, if there are any, that are in the equation. So let's look at example 4. What we want to do is solve the equation for the basic variable in terms of the free variables. Our first equation the basic variable is x1, and our free variables are x2 and x4. So we'll solve that. We'll get x1 equals negative 6x2 minus 3x4. And then we remember that x2 is free. And so now our second equation, we're going to solve for x3, which is a basic variable. So we have x3 equals 5 plus 8x4, and x4 is free. And then we have our last equation, which is already solved for our basic variable x5. x5 equals 7. So these sets of equations then are called our general solution. The general solution of the system provides a parametric description of the solution set. The free variables then act as parameters. For example 5, I want you to try. I want you to find the general solution of the given augmented matrix. So the first step is to get it into reduced echelon form, which means that you're going to need to look at your pivots, and make sure that you have zeros up above them. And once you do that, then write it in equation form and solve those for the basic variables. And we'll talk about those in class. A caution: the following system is in echelon form but is not in reduced echelon form. The backward phase of row reduction to reduced echelon form is equivalent to back substitution. It's important that you use only the reduced echelon form to solve a system. Now we want to answer some questions about existence and uniqueness. For example 6, we want to determine the existence and uniqueness of the solutions to the following system. In example 3, we obtained the echelon form of the augmented matrix for this system, and so we have it here. Notice that column 1, 2, and 5 were our pivot columns, and then we have free variables at x3 and x4. We see from this echelon form that there are no equations of the form 0 equal 1, so then the system is consistent. And there are two free variables. They are x3 and x4. So when we have a consistent system with free variables, we note that there are infinitely many solutions. When we say we have a free variable, that means that we can choose any value for x3 or x4 and get a different solution when we plug them in. So that means we have infinitely many solutions. Now let's look at another example. We want to determine the existence and uniqueness of the solutions to this system. First we'll write it as a matrix. So we have 3, 4, negative 3, 2, 5, 5, and negative 2, negative 3, 1. And we begin to get it in echelon form. So the first step, I'm going to multiply by negative 2/3 and add it to the second row. And then I'll multiply by a positive 2/3 and add to the third row. So I get the following matrix. And now my 7/3 is my pivot, so I want to get a 1 there just because it's going to be easier to work with than the fraction. So I'll multiply row 2 through by 3/7. And now I want to get a 0 where the negative 1/3 is. So I'm going to multiply row 2 by 1/3 and add it to row 3. So this matrix is now in echelon form, and I'll convert it to equation form. I'll have 3x1 plus 4x2 equals negative 3, and then I have x2 equals 3, and my last line will be 0 equals 0, which is a true statement. So we see that we don't have a case where we have 0 equals a number, so we know that this system is consistent, and we have a consistent system then that has no free variables. Each variable, x1 and x2, is a basic variable. When that happens, then we have a unique solution. We'll have one answer. We see that x2 was equal to 3, and if I substitute that back in the first equation, I will then be able to solve for x1 and get a value for it. So I have one solution to the system. So it's consistent and unique. That leads us to Theorem 2, the existence and uniqueness theorem. Number 1, a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form all zeros and B, where B is not 0. If we had something where B was not 0, then we would end up with an equation of the form 0 equals a number, which means it's not consistent. Number 2, if a linear system is consistent, and this is what we looked at in examples 6 and 7, then the solution set contains either 1, a unique solution, as we saw in example 7, when there are no free variables, or 2, infinitely many solutions, as we saw in example 6, when there is at least one free variable.